Hopefully in class we got up through talking about rate constants called K and how to determine what their units are going to be for any possible rate law problem. As we continue on, we're now going to look at this thing called the integrated rate law. The integrated rate law is a calculus-based way of looking at these types of reactions. Now, in the previous information, we had talked about first order reactions, we had talked about second order reactions, and we had intimated, but we didn't actually talk about something that was a zero order reaction. These are pretty much all we're going to talk about today in this little lesson, but at the same time, there are other things that are out there. We're just not going to be dealing with them in a first year chemistry class because it's not that important. Essentially, here's what happens. If we do calculus, we can change what we used to have as our rate law. Remember, the previous rate law was rate equals the K times concentration of A to some power times the concentration of B to some different power. Remember, we talked about that. This is not integrated. Okay, the integrated rate laws are going to be what we write over here. An integrated rate law comes from calculus. It's talking about instantaneous data. And so what ends up happening is when we look at the first order integrated rate law, it is a different mathematical function. It is the natural log of the concentration of whatever the reactant is at time t, that's the time we're looking at it, divided by the concentration of the reactant at time 0, which is the initial concentration. That natural log will be equal to the negative, still the same K, rate proportionality constant, times t for whatever that time is going to be. Now recall from Algebra 2, natural log is ln. That natural log is an important concept that we need to know about. So to think about what's going on here, we have to think of the whole entire reaction process. If I were looking at this as time is taking place going this way, and these are the reactants, so we're looking at how the change of this stuff is going to happen. So if this is concentration, we're starting with a high concentration, right? At time 0, I have however much stuff I started with. In a first order rate law, what we're going to say is that the way that the concentration changes is going to be, it's always going to look the same. So what's going to end up happening is graphically, this is going to look something like this. And if you guys remember anything, those of you that have been in calculus or in algebra, not so much algebra 2, but like pre-calculus and stuff, when we look at this curve that looks this, it's a logarithmic curve. And that's what this natural log is saying. So what we want to look at is when we start the reaction, we have a certain amount of concentration of R. But as time goes by, that reactant is going to go away. It's going to be turning into products. So that when new products are being formed, if we were to look at products being maybe a purple line instead, at time 0, we don't have any product. But as the reaction takes place, it's going to increase until it flattens out. And both of these lines, both the increase of products being made and the reactants going away, will sooner or later come to the same place, where, not the same place, but they're both going to be changing at the same rate, meaning my reaction has stopped taking place. So what we're looking at here is if we know the concentrations at a given time, so say at time 5 seconds, right, is going to be right here. If I know what the concentration was at time 0 and at time 5 seconds, then I can figure this stuff out. So all we're really going to do is we start the reaction, it starts going, we know what we initially started with, and at some given amount of time we say stop, how much do we have? Now in order to figure this out, we have to know that it's a first order reaction. If it's not, then we can't do anything about this. Most of the time, the whole idea of this is we know, oh, this is known to be a first order reaction. So again, if we know the concentration of R at time t and the concentration of R at time 0, then we can find K. If we know the concentration of R at the beginning and the value of K, then we can find the concentration of R at some given time. And if K is known, K is known, then the time elapsed to a specific quantity. I'm actually going to say a specific fraction of RT, oops, that's supposed to be on the outside, oh well, to R0. Those are supposed to be on the outside of the brackets. Then we can find that fraction. And now for first order reaction, the units on K, we talked about this before. Remember, and we should have talked about this in class on Monday, the units on K for a first order reaction will always be 1 over the time. That could be 1 over seconds, it could be 1 over hours, it could be 1 over minutes, it's whatever that unit of time is going to be. So now in order to do these problems, we have to think about it by looking at actual data. So let's do a practice problem. So here's our problem. We're going to take sucrose and let it decompose in an acid to form glucose and fructose. Now the chemical reaction we didn't really care about because remember that the order of the reaction is not related to any balanced equations or anything like that. The order of the reaction is found experimentally. Now they're telling us this is first order. They give us the value of K and they want us to figure out what the new concentration will be after 5 hours if I start with a given concentration of 0.01 molar. Now remember that's 0.01 moles per liter. Molarity is all the same. Since this is a first order reaction and they're giving us some information, we're going to use that equation we just talked about. The natural log of the reactant at time t divided by the concentration of the reactant initially is equal to negative KT, where we can solve for all these parts. So if we were to take this information and just plug in what we know, it becomes a really easy mathematical problem. So we're going to take the natural log of the unknown, that's R at time t, that we want to know, what the concentration is going to be after 5 hours. The initial concentration was 0.01 molar. That is equal to negative, the value of K was 0.21. And since in this case our T is going to be in hours, we just put 5 for 5 hours. So this becomes algebra with a little bit higher level that you need to understand what happens algebraically with what's happening here. Do you know how to get rid of a natural log? This natural log thing that we're looking at right here, natural log can be gotten rid of by an inverse natural log. So this fraction is also like it's subtraction. There's a whole bunch of stuff going on. So we're just going to start simplifying. Natural log, I'm not going to write the sub t. 0.01 equals, when we do this mathematically. So now algebraically speaking, we're going to take the inverse log of both sides, which in this case is going to be e, because it's a natural log, to that power. So e to that power on your calculator. This is going to give you the concentration of R over 0.01 is equal to 0.35. So at that case, now we just have to do algebra to solve for R, and the concentration of R at time t is going to be well, let's use scientific notation because that's going to be easier. 3.5 times 10 to the negative third molar. So a second order equation has a little bit different of a mathematical equation to be able to solve for. In this case, we're going to take 1 over the concentration at time t, that would be here, 1 over, minus the concentration of 1 over the concentration at time 0, and that will be equal to a positive. That's supposed to be a positive sign. It looks like a t. So we'll just leave it as just KT. It's positive this time. Remember, before it was negative. So in other words, the concentration at whatever time, 1 over that concentration minus the 1 over concentration gives you a positive value now. You're going to do the same stuff. You still do algebra. We get to figure out what's going on here mathematically and solve for the given values. And again, this just becomes algebra problems. Understanding what's taking place inside the chemical equation or inside the chemical reaction is key here. In a second order reaction, the amount of reactants is changing a little bit more rapidly because it's second order. Remember, if we doubled the concentration, we doubled the reaction, or if we doubled the reaction rate, we fourpled the. See, I already messed up. Let me say that again. If I doubled the concentration of a reactant, I would quadruple the rate of the reaction. That's a second order reaction. So what happens algebraically when we start going even higher, it's not even algebra anymore. When we get to calculus, this is the equation that comes out. It becomes plugging in the values, doing math, and solving for whatever's missing. Now finally, a zero order reaction, if you remember, that would have an exponent of 0, which means if I change the concentration of that reactant, nothing happens to the rate. The rate continues to be the same. That would be a zero order reaction. So the formula to solve that is, as we see here, whatever my initial concentration was, minus my new my new concentration at times T is going to be equal to KT, where K is still that same proportionality constant. We still can just do algebra to figure this out because it's a lot simpler in the sense that we know that whatever I started with, it's going to keep decomposing. It's going to keep going away, that one reactant, into whatever you're forming at a zero order. Now again, most of these reactions are going to be whatever my reactant is going to be decomposing into products. It's almost always only one reactant when we're looking at first order reactions. Or sorry, not first order, when we're looking at integrated rate laws. Integrated rate laws typically look at one reactant becoming some number of products because we're going to compare the rate that that substance is going away. That's the rate of the reaction. In the other kind that we were doing in class on Monday, a lot of times for those, yes, we look at the reactants and how they're reacting and whether more or less are being formed. So that was the ones like A plus B forming some product. So in these cases, we want to see how these reaction concentrations affect the formation of the product. But when we start to do the integrated rate law, it's typically A becoming some product. And I've been using R because that's reactant. That's what we did there. Hopefully this is a little bit easier to understand. When I keep going on section 3 of this little introduction of stuff, we'll talk about half-lives and first order processes, and then we'll also talk about reaction mechanisms.